So let's look more generally at this idea of an object falling and see how it illustrates conservation of energy. So let's say that this object starts out and it has an initial potential energy of 100 joules. Okay? So just based on whatever its mass is and whatever its initial height is, it has a potential energy of 100 joules. Now, if I drop this object from rest, its initial kinetic energy would be 0 joules because, again, since kinetic energy is 1/2 mv squared, if the object isn't moving, it has no kinetic energy. Now, let's look at what happens when the object has fallen to half of its initial height. Since potential energy, sorry, I should put Ke there. Since potential energy is mgh, once this object has fallen to half of its original height, it will only have half as much energy as it started with. So the question is, how much kinetic energy will the object have at that moment? Well, the answer is that it will have 50 joules. And this is what we mean by conservation of energy. The total energy doesn't change, but it can change from one type to another. So we know what happens when I drop the object. It starts to speed up. So as it's losing potential energy, it's gaining kinetic energy. So the potential energy is being converted into kinetic energy. Okay, let's look at the object just before it hits the ground. So when it's just about to hit the ground, the potential energy is basically 0. At that point, then, the kinetic energy would be 100 joules because all of the potential energy has been converted to kinetic energy. Okay? So this is the instant that it gets to the ground. Now, once it hits the ground, the energy gets transferred to the ground. And so we're not talking about that part. We're talking about right before it gets to the bottom. Okay? So that's an example of conservation of energy. Here's another example. Let's say that I have a roller coaster. So let's say again that I've got my little roller coaster car, and here's my ground level. Let's say that it starts out with a potential energy, again, of, let's say, 1,000 joules this time. And let's say that it initially starts out from rest, so that it's not moving initially, it doesn't have any kinetic energy. As the cart comes down, it's going to start losing potential energy and gaining kinetic energy. So when it's down here at the bottom of the track, it would now have no potential energy, and it would have all kinetic energy. Now, if we look at some point else along the track, let's say that when the cart is right here, I tell you that it has 250 joules of potential energy. How much kinetic energy would it have at that point? Well, hopefully you got that right. The correct answer would be 750 joules. And again, notice that the total amount of energy is always 1,000 joules. So again, the total amount of energy doesn't change. Energy is just converted from one type to another. Let's talk about what we mean by power. Power and energy are two terms that are often used somewhat interchangeably in everyday language, but they mean very different things. Power is the rate at which we use energy, or the rate at which we do work. So in other words, it's work over time, or energy over time. Let's look at what the units of power are. We know that the units of energy are joules, So when we take energy and divide by time, we get joules per second. And power is an important enough quantity that we give it its own unit, which is the watt. Now, you've all seen watts in your house before, and if I ask you, where do you see watts in your house, probably the most common answer would be on a light bulb. So for example, if you have a 100-watt light bulb, what that's telling you is that light bulb uses 100 joules of energy for every second that it's turned on. And you remember earlier I referred to the fact that a joule is a fairly small unit of energy, and you can see that here because if you only leave your 100-watt light bulb on for 1 second, you've already used 100 joules of energy. If you leave it on for 10 seconds, you've now used 1,000 joules of energy. Okay? So power is the rate at which we do work or the rate at which we use energy. It's just energy per time. Let's talk about heat, or what we also call thermal energy. In order to understand heat or thermal energy, we have to remember that all matter is made up of atoms and molecules. And remember, a molecule is simply a combination of two or more atoms. Well, when an object becomes warm, when we heat up an object, what's actually going on at the atomic or molecular level is that the atoms are beginning to move or vibrate more. And they can do a couple things. They can start jiggling back and forth so they can vibrate, they can rotate, they can move, like the molecules in a gas can just move freely. Molecules in a solid can vibrate. So that motion is what's happening when we heat up an object. Okay, so an object that's hot, simply the atoms in the molecules have more kinetic energy than they did if the object is cooler. Let's look at how heat or thermal energy can be transferred. There are three ways that heat can be transferred, and they're called conduction, convection, and radiation. And this diagram gives you a quick sense of what they are, but I'm going to talk in a little bit more detail about each one. Convection has to do with the fact that either air or really any gas or any liquid, when it gets warm, it will tend to rise. And so you've all heard the expression hot air rises. That's talking about convection. So our person putting their hands up above the fireplace, their hands get warm because of the hot air rising. That's convection. Conduction is the fact that if you are holding on to an object and the object is a good conductor, heat can be transferred along that object. And in this case, that's showing a metal poker. Metal is a good conductor, and so heat actually gets transferred through the metal very efficiently. And I'm sure you've all experienced that. You put a metal spoon in something hot, and the handle of the spoon gets hot quickly. That's because the energy transferred through the spoon. And then finally, we have radiation. And let's say that I have a glass door in front of this fireplace. So there's no convection. I'm not touching anything, so there's no conduction. And yet if I hold my hands anywhere near those glass doors, I'll still feel heat. And that's from radiation. So those are the three types of ways that heat can be transferred, and we'll now talk about each of them in a little bit of detail. So for conduction, here's a question. Would you rather use a pot with a metal handle or a plastic handle? And I think everybody would say a plastic handle, and that's because plastic is not a good conductor. So when we talk about conduction, we mean the transfer of heat or thermal energy either from direct contact between two objects. For example, if you touch something that's hot, you're feeling that heat through conduction, or transfer within an object. So we know, for example, that the metal handle of a pot is going to transfer heat very efficiently, and therefore the handle of that pot is going to get hot. So metals are very good conductors of heat. Other materials are good insulators. So for example, styrofoam is a good insulator, which is why, if you go and buy a cup of coffee, chances are it's going to come in a styrofoam cup so that it's not uncomfortable to hold, even though the liquid inside it is very hot. And again, the way it would get hot is through conduction. Okay, convection is heat transfer via movement of liquids or gases. And let's talk about how this happens. Basically what happens is when molecules in a fluid, and fluid, by the way, means liquid or gas. When molecules in a liquid or gas are moving faster, they tend to spread apart. They're bouncing around more. And therefore, they become less dense, and something that's less dense is going to rise. So whether it's in a liquid or in a gas like air, the hot air is going to rise. And by the way, this is how it works to heat your home, by just having a radiator on one wall of your house. So for example, radiators, you'll notice, are always along the outer wall of a house. What happens is the radiator gets hot, and so the air above it becomes less dense, and it starts to rise. And then that air basically travels across the ceiling. As it begins to cool off, it begins to fall. And so you get this natural circulation of air throughout the room as the air gets warmed by the radiator. Let's talk about radiation. We've already talked briefly about what we mean by radiation. Specifically here we mean electromagnetic waves. And this is the electromagnetic spectrum that we talked about briefly already, and we'll be spending a lot more time on, because of course this is why you guys are in the course, because you need to know about X-rays, and X-rays are part of the electromagnetic spectrum. Remember that whether we're talking about radio waves or microwaves, infrared, visible, ultraviolet, X-rays, or gamma rays, all of that is really the same stuff. It's just electromagnetic waves. And what differentiates one type of radiation from another is simply the frequency of those waves. Okay, so it turns out that every object that's at a temperature above absolute zero, and that basically means everything, gives off thermal radiation. It gives off electromagnetic waves. So in fact, right now, as you're sitting there watching this presentation, you are emitting electromagnetic waves. Now, obviously, you're not emitting visible light, but you are emitting a type of electromagnetic radiation. And it turns out that the frequency of the radiation given off by an object is proportional to its temperature. So the hotter the object, so if the object is hotter, then the frequency that it gives off is higher. Now, for an object that's at room temperature or body temperature like you and I are, we emit infrared radiation. So we can't see it. It's below the visible part of the spectrum. But as something gets hotter, it can give off visible light, and that's how an electric light bulb works. So as the filament gets hot, it's giving off visible radiation. Now, one of the things you've probably noticed is if you turn on the burner of an electric stove, what you'll notice is it will glow red. And the reason is that the temperature of that stove is not as hot as the filament of a light bulb, so it's just getting out of the infrared part of the spectrum and into the red part of the spectrum. And just to illustrate that back here, in other words, an object that is at room temperature is emitting in the infrared part of the spectrum. As I start to raise the temperature of that object, the frequency it emits goes up. So the first part of the visible spectrum that it would get into is the red part of the spectrum, and that's why it would emit red light. Once it gets hotter, it emits across the entire visible spectrum, and that's what we see as white light. And so that's why a light bulb gives off white light. Okay, so that's the three ways that energy can be transferred: conduction, convection, and radiation.